Replacing a wye-wound motor with a delta-wound motor is generally not recommended due to differences in the winding configurations and electrical characteristics. A wye-wound motor has its windings connected in a Y configuration, where one end of each of the three windings is connected to a common point, often called the neutral point. The other ends of the windings are connected to the three phases of the power supply. This configuration provides a specific relationship between voltage and current in the windings. Specifically, the line voltage, which is the voltage between any two phases, is equal to the square root of 3, or approximately 1.732 times the phase voltage, which is the voltage across each individual winding. The line current, which is the current flowing through the power supply lines, is equal to the phase current, which is the current flowing through each individual winding. In a delta-wound motor, the windings are connected in a triangle configuration, where each winding is connected between two phases of the power supply. In this configuration, the line voltage is equal to the phase voltage. However, the line current is equal to the square root of 3, or approximately 1.732 times the phase current. Because of these fundamental differences in voltage and current relationships, a wye-wound motor and a delta-wound motor cannot be directly interchanged. If a delta-wound motor is connected to a Y-connected power source or vice versa, the motor will not operate correctly and could be damaged. Specifically, the motor may experience overvoltage or overcurrent conditions which can lead to insulation breakdown, winding failures, and other types of damage. The speed of the motor is also affected by the winding configuration. For the same number of poles and supply frequency, a delta-wound motor will typically run at a higher speed than a wye-wound motor. This is because the back electromotive force, also known as back volts, which is the voltage generated by the motor as it rotates, is different for the two configurations. The back volts opposes the applied voltage, and the difference between the two determines the current flowing through the motor windings. Since the delta-wound motor has a higher back volts, it requires a higher applied voltage to achieve the same current and therefore the same torque and power output. When replacing a motor, it is crucial to consider the original motor's winding configuration, voltage, horsepower, speed, frame size, and other critical specifications. Using a motor with a different winding configuration can cause significant problems, especially when the motor is driving a specific load, such as a hydraulic pump. A hydraulic pump is designed to operate at a specific speed and torque to deliver the required flow rate and pressure. If the motor's speed is too high or too low, the pump may not function correctly, leading to reduced performance, increased wear and tear, or even damage to the pump or the system it serves. Therefore, if the original motor is a wye-wound motor, it is essential to replace it with another wye-wound motor that meets the same specifications. If a delta-wound motor is used instead, it is necessary to ensure that the power supply voltage and frequency are compatible with the motor's nameplate ratings, and that the motor speed and torque characteristics are suitable for the hydraulic pump. In some cases, it may be possible to use a variable frequency drive, also known as a volts drive, to adjust the motor's speed and torque to match the requirements of the hydraulic pump. However, this requires careful consideration of the volts drive's capabilities and limitations, as well as the motor's and pump specifications. It is also essential to ensure that the volts drive is properly installed and programmed to provide the correct voltage and frequency to the motor. In general, it is always best to consult with a qualified electrician or motor specialist before replacing a motor with a different type or configuration. They can assess the specific application requirements, evaluate the available options, and recommend the most suitable motor for the job. They can also ensure that the motor is properly installed and connected to the power supply, and that all safety precautions are followed. Additionally, it's worth noting that dual voltage motors can be wired in either a Y or delta configuration, depending on the specific voltage being used. When wiring a dual voltage motor, it is crucial to follow the manufacturer's instructions and the wiring diagram provided on the motor's nameplate. Incorrect wiring can lead to motor damage or failure. Finally, always ensure that the replacement motor has the same or higher horsepower rating as the original motor. A motor with a lower horsepower rating may not be able to handle the load, leading to overheating and premature failure. In summary, replacing a wye-wound motor with a delta-wound motor is not a straightforward task and requires careful consideration of various factors. It is generally best to replace the motor with the same type and configuration, or to consult with a qualified electrician or motor specialist to ensure that the replacement motor is suitable for the application. When working with electrical equipment, always follow proper safety procedures and wear appropriate personal protective equipment, such as gloves and safety glasses. Always disconnect the power supply before working on the motor or its wiring, and ensure that the motor is properly grounded to prevent electrical shock. Remember, electrical work can be dangerous, and it is always best to err on the side of caution. If unsure about any aspect of the job, seek the assistance of a qualified professional. Furthermore, ensure the replacement motor has the same frame size as the original. The frame size determines the motor's mounting dimensions and shaft height. A different frame size may require modifications to the mounting base of the pump coupling. It is important to also consider the motor's enclosure type. Enclosure types include open drip proof, totally enclosed fan cooled, and explosion proof. The enclosure type should be appropriate for the environment in which the motor will be operating. For example, a motor in a dusty or wet environment should have a totally enclosed fan-cooled enclosure to protect it from contaminants. Also make sure to check the motor's service factor. The service factor is a multiplier that indicates the motor's ability to handle occasional overloads. A motor with a higher service factor can handle larger overloads without overheating. When selecting a replacement motor, consider the motor's efficiency rating. High-efficiency motors can save energy and reduce operating costs. Efficiency ratings are typically expressed as a percentage, with higher percentages indicating greater efficiency. Verify the motor's ambient temperature rating. The ambient temperature rating indicates the maximum temperature at which the motor can operate without overheating. If the motor will be operating in a high-temperature environment, choose a motor with a suitable ambient temperature rating. Before installing the replacement motor, inspect the wiring and connections. Look for any signs of damage or corrosion. Replace any damaged wiring or connectors. Use the correct size and type of wire for the motor's voltage and current requirements, consulting NEC Table 310.15b16 for ampacity. Ensure that all connections are tight and secure. Loose connections can cause overheating and voltage drop. When connecting the motor to the power supply, follow the wiring diagram provided on the motor's nameplate. Incorrect wiring can damage the motor or create a safety hazard. After installing the replacement motor, test its operation. Check the motor's voltage, current, and speed to ensure that they are within the specified ranges. Listen for any unusual noises or vibrations. If the motor is driving a hydraulic pump, check the pump's flow rate and pressure to ensure that they are within the specified ranges. If any problems are detected, troubleshoot the motor and its wiring. Correct any problems before putting the motor into service. Regular maintenance can help to extend the life of the motor. Inspect the motor regularly for signs of wear or damage. Lubricate the motor bearings as needed, following the manufacturer's instructions. Clean the motor's cooling vents to prevent overheating. Keep the motor area free of debris and obstructions. By following these guidelines, one can ensure that the replacement motor operates safely and reliably for many years. Remember that working with electrical equipment can be dangerous, and it is always best to consult with a qualified electrician or motor specialist if you have any questions or concerns. They can assess the specific application requirements, evaluate the available options, and recommend the most suitable motor for the job. They can also ensure that the motor is properly installed and connected to the power supply, and that all safety precautions are followed. In addition to the winding configuration, voltage, horsepower, speed, frame size, enclosure type, service factor, efficiency rating, and ambient temperature rating, there are other factors to consider when selecting a replacement motor. These include the motor's starting torque, breakdown torque, and pull-up torque. The starting torque is the torque that the motor can produce at startup. The breakdown torque is the maximum torque that the motor can produce before it stalls. The pull-up torque is the minimum torque that the motor can produce as it accelerates to its operating speed. The starting torque, breakdown torque, and pull-up torque should be sufficient to meet the requirements of the load. For example, a motor that is used to start a high inertial load, such as a fan or a compressor, will need to have a high starting torque. A motor that is used to drive a load that is subject to sudden changes in torque will need to have a high breakdown torque and pull-up torque. It is also important to consider the motor's insulation class. The insulation class indicates the motor's ability to withstand high temperatures. Motors with higher insulation classes can operate at higher temperatures without damage. The insulation class should be appropriate for the environment in which the motor will be operating. For example, a motor that is used in a high-temperature environment, such as a steel mill or a foundry, will need to have a high insulation class. When selecting a replacement motor, it is also important to consider the motor's bearing type. Motors can have either ball bearings or sleeve bearings. Ball bearings are more durable and can handle higher loads than sleeve bearings. However, ball bearings are also more expensive than sleeve bearings. The bearing type should be appropriate for the application. For example, a motor that is used in a high-speed application or high-load application will need to have ball bearings. In addition to these factors, it is also important to consider the motor's cost, availability, and lead time. The cost of the motor should be within budget. The motor should be readily available from a reputable supplier. The lead time should be acceptable. By considering all of these factors, one can select a replacement motor that is suitable for the application and that will provide many years of reliable service. Furthermore, it's essential to verify the motor's nameplate data against the system requirements. The nameplate provides crucial information, including voltage, current, horsepower, speed, frequency, and other relevant parameters. Mismatched parameters can lead to inefficient operation, overheating, or even motor failure. When dealing with dual voltage motors, carefully examine the wiring diagram to ensure correct connections for the desired voltage. Incorrect wiring can damage the motor and pose a safety risk. Always double-check the connections before energizing the motor. Also, remember to properly ground the motor to prevent electrical shock hazards. A good grounding connection provides a path for fault current to flow, tripping the circuit breaker and preventing dangerous voltage buildup. Use a grounding conductor of the appropriate size, as specified by the National Electrical Code (NEC). Consider using a surge protector to protect the motor from voltage spikes and transients. Voltage surges can damage the motor's insulation and shorten its lifespan. A surge protector can help to absorb these surges and prevent damage. Finally, remember to document the motor replacement process. Keep records of the old motor specifications, the replacement motor specifications, and the wiring connections. This documentation can be helpful for future maintenance and troubleshooting. When the motor is driving a hydraulic pump, consider the pump's specific requirements. The motor's speed and torque must be compatible with the pump's operating range. Using a motor with the wrong speed or torque can damage the pump or reduce its efficiency. Consider using a variable frequency drive, volts drive, to control the motor's speed. A volts drive allows you to adjust the motor speed to match the pump's requirements, optimizing performance and efficiency. When selecting a volts drive, consider its voltage, current, and horsepower ratings. The volts drive must be able to handle the motor's voltage, current, and horsepower requirements. Also, consider the volts drive's features and functionality. Some volts drives offer advanced features such as automatic energy optimization, pump control, and fault diagnostics. When installing a volts drive, follow the manufacturer's instructions carefully. Incorrect installation can damage the volts drive or create a safety hazard. Finally, remember to properly program the volts drive to match the motor's and pump's characteristics. Incorrect programming can lead to inefficient operation or damage to the motor or pump. Also, consider the motor's cooling requirements. Overheating can damage the motor's insulation and shorten its lifespan. Ensure that the motor has adequate ventilation and is not located in a confined space. Clean the motor's cooling fins regularly to remove dust and debris. Consider using a motor with a thermal overload protector. A thermal overload protector will trip the circuit breaker if the motor overheats, preventing damage. Before energizing the replacement motor, perform a visual inspection of the wiring and connections. Look for any loose wires, damaged insulation, or signs of corrosion. Tighten any loose connections and replace any damaged wire. After energizing the motor, monitor its operation closely. Check the motor's voltage, current, and temperature. Listen for any unusual noises or vibrations. If any problems are detected, de-energize the motor immediately and troubleshoot the problem. Also, it is important to consider the motor's operating environment. If the motor will be operating in a harsh environment, such as a dusty, wet, or corrosive environment, choose a motor that is designed for that environment. Motors that are designed for harsh environments typically have special enclosures, coatings, and seals to protect them from the elements.